All right. Is it coming on? There we go. Make sure the HDMI is in there well. Why is it not Okay. I'm used to my other. I don't use this very often. I'm used to my other classes where we have this. Okay. So we want to do some work today. Literally, we're going to talk about work, and I know life is work. I'm from German heritage. I don't mind work. We have 20 different words for work. We just love work. Okay, so work, first of all, to understand what it is, okay, here's one definition of work, okay? So we can define work like this. We can say that work is equal to force times distance. And that's a legitimate definition. You can also start from the definition that work is the change in energy of a body, okay, when it's acted on by a force. And we all kind of saw that. When we looked at those graphs and looked at acceleration and velocity, everyone totally got the idea that when the force is acting on the body, it's changing the velocity, which is changing the kinetic energy. Okay. Now, there's a little trick with this definition that to be careful about. First of all, we're assuming that the force is constant. Okay, so this is the force exerted on the body. Okay, force exerted on the body. This is the distance the body has moved. Okay. But there's another little implicit fact here, which is that we're assuming that the force is going in the same direction as the body's moving. Okay. So the force is being applied in the direction that the body is moving. So this is a force exerted on the body in the direction of the body's movement. Okay. In other words, it's the component of force along the direction of motion. And so all of you, I'm sure, are used to this sort of figure, right? Where you have some sort of net force. Okay, this body moves a certain distance d in this direction. This is the total force, and of course the relevant force here is the component of force in the direction of the body. So that's what we're saying, all right? Good. And one last thing, we have to be careful. This is when the force is constant. Okay, so it's the force exerted on the body in the direction of the body's movement, and the force is constant. All right? Okay, so this is probably stuff that everyone pretty well knows. Now, one thing we have to be a little careful about, we have to watch units. Units get a little tricky. So there's two different types of units. One is the MKS, the meters, kilograms per second, right? And in this unit, in this system of units, the unit of mass, and that's how we represent units by a little bracket. This is a kilogram. The unit of force is a kilogram meter per second squared, affectionately known as a Newton. And the unit of work is 1 Newton meter, also known as a joule. Now, that's the one that we like to work in, and most physicists that. But occasionally, you know, the British, they have this imperial system, right, or the British system of units. It's now called the imperial. It's a lot more complicated and cumbersome. So the unit of mass in the British system is slug. Which, you know, who uses that, right? Force is in pounds, and work is in foot-pounds. Okay. So the thing you want to be really careful of, all all of you, I'm sure, are pretty familiar with the S system. When you're given the forces, you're given that something has a certain weight in pounds, you know, that's any questions on the basics so far? Everybody's good. So I want to look at two different scenarios. The first scenario is a scenario where the force is constant. And we're just going to apply this formula, okay, using these different types of systems. So if you look at the first problem in the notes, right, the first problem we have a book. So this is example 1. In part A, we have some book. Okay, and let me get the numbers right here. We have a 1.2 kilogram book. Okay, and we want to raise it up to a desk that's 0.7 meters above. And we want to know what's the work required. All right. So let's go ahead and use our formula, right? So the work is equal to force times distance. I gotta be careful. Is the force constant here? The force acting on the book? It is. Because what's the force? Gravitation, right? So the gravitational force here is m times g, right? The distance is 0.7 meters. That's our distance. And I can just go ahead and plug these in, right? So 1.2 times 9.8 times 0.7. Well, I'd be a little careful about the units, okay? So I need a little cavalier here, and the only reason why is because I know that these units are all the same, right? This is kilograms, this is 9.8 meters per second squared, that's the gravitational constant, and this is 0.7. Get a little lax with that. And if you compute that out, you end up getting 8.232 joules. Okay? That's not too bad. And I'm sure you've done problems like that in physics. Is there anyone here that doesn't have physics 1? I'm kind of assuming everyone has. Okay. 1, 2. All right, a few people. Okay. So now you know the sort of problems that you'll be doing in physics 1. This is all you're doing pretty much. Right? It's a little harder than that. Okay, so part B is now switching over to the English system. So it says, okay, suppose you have a book that's 20 pounds. I've had a few of those. Okay, so this is 20 pounds. And now you want to raise it a distance of 6 feet. Okay, how much work is required? And that's pretty easy because 20 pounds is not the mass, it's the force. Okay, so this is literally the force. So the force here is 20 pounds, the distance is 6 feet, and so the work is easy to compute, right? Foot-pounds. And that's that, and that's the work. All right? So now we're going to deal with more interesting problems. Now I want to deal with problems with forces no longer constant. That's the general scenario. So gravitation is one of the few examples where the force is constant, all right? But before we get on to the more complicated ones, any questions on this notation, things that, because there are a few people who don't have physics, everyone's good with, let me just write down a few things that we might want to emphasize. So G is just the gravitational constant, just 9.8 meters per second squared. It's the acceleration due to gravity, okay? All right, so let's move on to some fun problems. So the first problem I want to look at is the problem of a spring. Sometimes people call this an elastic spring. So here's kind of the scenario that we have here. We have some sort of support, and we have a spring attached. And it's attached to some point mass. And this is at rest. So the spring is just sitting. And one of the reasons I didn't think about point mass, right, I had this notion of center of mass, looking at gravitation center of gravity, would actually kind of feel physics. It says you can always replace the rigid body kinematics, called rigid bodies moving by just looking at a single point. Replace that entire body by a point having all that mass. Okay, so we can do that. So here's kind of the scenario. Now I want to stretch that spring. I could compress it, but I'm going to stretch it. And of course, anyone that's ever worked with a spring, you know that there's work involved, right? You have to exert energy. So this is the distance that the spring's been stretched. And I'm going to think of the resting spot as kind of like the origin, right? So this spring has been stretched some positive distance x. And people found out, the really cool thing is that people found out all these things here. He figured out how to make the force required when you stretch the spring. So when you have a spring at this distance, what force are you exerting on the spring? Okay. And it turns out that the force you're exerting on that spring ends up being k times x. If I were to hold the spring there, I have to obviously have some force, right, to hold it there. That's going to be the gravitational force. And this is called Hooke's law. This is called Hooke's law. Now, a few little pieces of information we might want to know about Hooke's law. First of all, it's not always true. It's only true when you don't stretch it or compress it too much. So Hooke's law is valid for what we call small deformations. Okay? So it's valid for small deformations of the spring. And what is K? Okay, it has a name, the spring constant, okay? So it's called the spring constant, you know, something. So what is it? It's a constant, obviously, right? What is that outcome? I mean, every spring doesn't have the same constant, right? So that's close. So what we're doing is stretching this the elasticity. I think it was kind of like the stiffness, right? So K is a measure of the stiffness of the spring. In other words, if you have two springs and you stretch them the same amount, the one takes a lot more force, right? But you have to go after the spring. And Hooke's law is actually really cool. You might say, well, this is kind of boring. But actually it's not. It turns out that almost this sort of solid physics of solid, what is called material science, really useful. So like, for example, I want to know, when I take this gas, how does this gas respond? The way to think that all the atoms will be connected by little springs. And when you put that force into the those springs, so this spring is gas carpet is really kind of that K, and that's really the bonds that are holding the atoms together. Stronger bonds, stiffer material. And this is something when you study sound waves or phonons, there's a whole field of modeling, like electricity. If you study quantum mechanics and charged particles, they all kind of can be used to analyze this model. Kind of cool. All right, so let's go ahead and work a problem. So in this problem, we're not interested in electrons, we're just interested in this humble mass. And we're told that a force of 40 newtons is required to hold a string that has been stretched from a natural length of 10 centimeters to 15 centimeters. So here's what we start with. So its natural length is 10 centimeters. Okay. And then I stretch it to 15 centimeters. And the force that I'm exerting at that time is 40 newtons. All right. Why did they give me all that information? They didn't even ask about work, right? That was about work. Why didn't they give that? Yeah? I'm going to find K, right? Because I'm told the force and I'm told the distance, so I can find K. So let's go ahead and find K. The claim is I can use this. So let's see. So we know that F is equal to Kx, right? So this means that K is equal to F over X. So that should just be 40 newtons over 5 centimeters, right? You have to be careful. So I have to be careful because this is really in centimeters, right? And I don't want to. So I'm going to have to go ahead and use 40 newtons, and this is going to be 0.05 meters. And then when I do that, I'm going to get what? 800 meters. Okay? That's my routing code. But be careful with units. Okay, so now I know everything about the force. I know that the force is equal to 800 x. And again, I'm assuming x is going to be a meter still, right? Okay, so now I'm given some additional information. Now I'm told, okay, the spring is now stretched from 15 to 18 centimeters. So here I was at 15 centimeters. I stretched it to 18, and I want to know how much work is required. So I stretched it this 3 centimeters, and I want to know how much weight is required to do that. So let's go ahead and think about it. So now we have to be a little more careful. Right? Will I Okay, so you might say, okay, well, I know what work is. Work is equal to force times distance, right? I have to be careful, right? Because the force is dependent on distance also. Okay. So here's kind of the picture. Let me kind of show you where we're going, because this is a useful picture to think about. Okay. And this is how we're going to start thinking about work. So suppose I have some force exerted over some distance, like I do here, from 15 to 18 centimeters, all right? Here's how I'm going to start to think about this. I'm going to divide this up into little subintervals. Okay. And I'm going to ask, what is the work required to move my system some little amount? Okay. So maybe this is the ith little subinterval. Okay. So I divided this up into all these little subintervals. And I want to know what is the work required at that point to move things outside. How do you think I'm going to do that? I'm kind of drawing the picture and doing it in a way. How do you think I'm going to do that? X is small enough, the force is kind of constant, right? Okay. And so on this little subinterval, the change in the work is going to be f of xi times delta xi on that little subinterval. So notice that work is an area. Okay. Does that make sense? And so how do I find the total work? I'm going to sum up all those little changes in work, right? Suppose I have n little subintervals, all right? So now you can see where and that should be the exact value for the limit. Okay? So, in the limit of n goes to infinity, or equivalently, the delta xi's all go to 0, this sum ends up going to an integral. And now you see something that's super cool. This thing goes over to this angle. And that's the actual definition of work. Notice that the force is constant. I'll do that. So now we're going to claim this is our new definition of work. This is the more general definition, right? So we're going to use this definition of work. We're going to say that work is defined as this definite interval. Okay, so let's go back to our problem. Okay, so in our problem, what? So if we go back to our problem, f of x was equal to 800 times x, and so all I have to do is integrate that, right? So the work is equal to, I had to be a little careful, again, for the same reason, I go 0.15 centimeters to the point, from 15 centimeters to 18 centimeters, right? And I want to express this in meters. And now I just go ahead and integrate that. So this is 800 times the integral here of x squared over 2. Okay. And when you put all the numbers in and all the arithmetic smoke clears, you're able to figure it out. Spring is pretty easy, right? So for a spring, if we just think about the formula we use, right, the work for a spring. And we see something really interesting, right? This is kx squared divided by 2, a to b. That's the increase in the potential energy that's put in. So anyhow, there's so many cool things we could talk about with springs. They're just really cool. But harmonic oscillators, you study harmonic oscillators. Oh wow, okay. All right, so let's move on though and talk about a hanging cable. Okay. These last two problems are atypical, so you really have to have focus on them. Certain things that when I was a student, I'm not so sure I would have seen it right away. Okay, so if we look at the next problem, it has to do with a hanging cable. Here's kind of the problem: we have some building, and we have a cable hanging off of it. This is our cable. And we're told the length of the cable is 100 feet. And its total weight is 200 pounds. And so what I want to know is if I have to drag that all the way up. These are the things that hurt a lot of people. How many people have ever seen the movie Man on a Wire? About the guy who walked across the college? None of you ever saw that. Oh, come on. Over the break, watch it. So just real quick, this French guy was I think it's called All right. So anyhow, it's like a documentary. Okay. So anyways, we want to figure out what's the work required, and here's our point of view. Okay. There's two things that are really important when you're solving. The first thing is we need our origin somewhere, right? So I'm going to define my origin to be here at the top, and it's arbitrary. You can put it wherever you want. But I'm going to put my origin here. And the reason why is that's going to be kind of a natural nature of how far I have to raise up the piece of cable, right? That's pretty obvious, and you guys might notice that the amount of work required to raise this portion is not the same We're going to slice this into what we call elements. So I'm going to take this cable, I'm going to blow it up, okay, and I'm going to slice it into little elements, little thin sections, okay. I'm going to call these little sections elements, and this is going to have some height, delta xi. This is the ith element right here. Okay. And obviously it's going to have some height xi. I'm going to ask for this little element, what's the work required to raise it? So I want to know what is Wi. Okay. Well, I know what this is. This is going to be the force that's acting on that element times xi. Because on each element, the force is going to be constant. So what do I know? I know the total weight and I know the length, right? So what I know from this problem is I know the weight per length. So I know it's 200 pounds and it's 100 feet long. And if I make the assumption that it's kind of a constant density, right? I have 2 pounds per foot. Okay? But how long is my little element? Okay? So now I'm going to say that the force acting on this element is going to be 2 times delta xi. Okay? It's 2 pounds per foot, and that's like delta xi. And this is something we want to talk about. Now I have an expression for that change in work, right? So I can now say that the work required for that ith element is just going to be 2 delta xi. And of course the total work is the sum of course, you can kind of see that what's going to happen, right? I'm going to go right to the end. Okay. So now if I pass to the integral, this goes from 0 to 100, 2x dx, and I just evaluate that. How we actually solve the overall problem. And it'd be challenging to solve this problem in another way. Okay? So let's go ahead and do it. This is easy. I know it's Saturday, but this is an easy one. And so I'm just going to do that kind of before. And this will be rough time. What am I doing? Foot pound, yes. That's it. This idea of cutting things up in little slices and asking what's the work, that's very, very useful way of thinking about it. Okay. So this is the hardest one, the last one, okay? All right. This is the problem dealing with an inverted cone. And we're told the dimensions of this cone is, I believe it's 4 meters. Radius at the top is 10 meters high. And we have water inside this cone. So there's water in the cone, but it's not totally full. I have my nice visual aids too. This is the extent of my drawings. When I was a student in grade school and high school, I got straight except drawing. I failed drawing and writing. And they thought I did it intentionally, but I didn't. This is a total of 8 meters. So here's the problem we have. We want to drain the water out at the level of the top of the tank. I want to drain all the water out. So I want you guys to play with this for a little while. So think about this essentially as density of water. And it's 1,000 kilograms per meter cubed. This is how we write density. This is what we write density. write densities in physics and engineering. Just remember this is a Greek letter for knowledge and what. Yeah, notice that there's that the element of volume I'm going to take a little slice. Okay. All right. What is the force? What is the element? Gravity is, and the force acting on this is going to be constant, right? So the force acting on this little element is going to be MIG. Now I need to figure out the mass. Multiplied by the volume. So we're a little bit closer, right? It's okay. So I know that mass is rho times the volume. But what is the volume of this little slice? Notice when you do on some all the approximate. So how did I think about little slice? Even though it didn't how would I approximate what the slice looks like, right? So the slice looks like this. To the best of my limited plan. Okay. It looks like a little Reese's cup, right? That bottom radius. Let's make it into a cylinder, right? So what if I said this? Let's approximate. I am. Yeah, we're good till a little before lunch. It says 10:43. No, we appreciate you stopping in. Okay, so why don't we go ahead and just approximate that by a little cylinder? Okay. And I know the volume of the cylinder, right? And then what's going to happen? As delta xi goes to 0, right, that thing is really going to encroach. Okay. All right, so the volume of the cylinder, this volume is approximately pi Ri squared times delta xi. All right, so let's just try to put this together. Where are we? Okay, so let's go ahead and look at this. So the force is equal to G times rho times pi Ri squared delta xi. That's my force, right? Now I got a problem. What's my problem? All of the problem. do a little bit of work here, okay, and figure out the radius in terms of x, because I want to integrate with respect to x. So let's go back. So now this is where the origin comes into play. So I have to express this in terms of x. All right. So let's just take a look at this for a second. All right. So here's my element here. I define my origin to be at the top, okay? So if I'm going to raise this x, what is this radius? Well, this height is 10 minus x, right? This height here. And this is my radius, right here. Okay? So these are the relevant variables. This is my height, this is my height, this is my radius. 10 minus x is my height, bar is my radius, and now I can solve for this using similar triangles, because my outer triangle is what? My outer triangle has 4 for the radius and 10 for the height. So now I can write this relationship. The radius of the big cylinder over its height is equal to the radius of the small cylinder over 10 similar time. So now I can go ahead and I can solve for r, right? R is equal to 2 times 10 minus x. Okay? Almost there. I can plug this now in for r, and I know that for that middle element, the work is going to be 4 times distance, right? Because the force is constant. Okay? That can have a constant force acting on it. So now I can use the fact that this is going to go from 2 to 10. This is going to be f of x dx. I'm sorry, yeah, f dx. Sorry, the work is going to be, yeah, let me go back to the Riemann sign. I'm sorry. Let me not be quite so hasty. Right. So the work to do this is going to be f of xi times xi. And we put this all together. This is going to be e rho I times 2/5 squared 10 minus x squared times x delta x. I'll put the i's in there. This part came from the r squared, right? So, we're not in the same way. This is a little more important. And now I just integrate it. I let the delta x's go to dx's and I integrate. Yeah. So my final answer should be, I'm going from a height of 2 to a height of 10. E rho I 4 over 25. 10 minus x squared over x. This is a good problem to kind of do on one quick word of advice. One of the things you'll find a lot. And then this will be a little easier, right? I'll just mention this really quick. So if I let y be 10 minus x, right, this will now go from so 10 minus that would be 0. It'll be g rho pi 4 over 25 y squared, and then x is going to be 10 minus 1. That might be a little easy. Sometimes you'll find that so I'm going to go ahead and post these notes in the video. Well, hope you enjoyed the lecture. I will see you on Monday. I would suggest you talk. Suggested problem, okay. They'll be odd that you can work on all.